is an integer. And in fact, since A and B are positive, do you agree that C also has to be positive? Why is that? Well, as I said, we'll prove the laws of signs for multiplication in abstract algebra next term. And by the way, I think registration starts Thursday. If you have any questions about what the various classes are, at least in mathematics, we can discuss it. But we're assuming the basic laws of arithmetic for number theory. So if C were negative, then since B is positive, B times C would be what? Positive times negative would be negative, and A would be negative. It's not. So C has to be positive, and then I have a colon there, meaning C has to be, if it's positive, the smallest positive number is smallest positive integer is 1. So C has to be at least 1. And we showed at the beginning of the term that if you multiply both sides of an inequality, this is weak inequality because it's not strict inequality, it's greater than or equal to. But so we showed that if we multiply both sides by the same positive number, you preserve the inequality. So you get BC is greater than or equal to B. But I think you can see what's happening. A equals BC. So A, instead of BC being greater than or equal to B, A is greater than or equal to B. And that's what we wanted to show. Okay, so on the basis of that, we can show that every positive integer either is already a prime or it has a prime factor. Let's observe that this is true for all integers other than positive and negative 1 and 0. Remember, 1 is not, and we'll see why shortly. I mean, not today, but hopefully Thursday. 1 is not considered a prime, and it's also not a composite. It's called a unit, U-N-I-T. So notice that it suffices to prove this. I mean, it's true for all integers other than positive, negative 1 and 0. For positive integers, since a negative integer is -1 times a positive integer. Okay, so let's see why this is true. So let's take a number, say n, which is a positive integer. Well, of course, if n is itself a prime, there's nothing to prove. So we're trying to show that every number n is already a prime. Well, if it's already a prime, it's a prime. So there's nothing to prove. Okay, if not, let's be a little more careful here. Every positive integer greater than 1. Again, because 1 isn't a prime and it's not a composite. So every positive integer greater than 1. So if n is not a prime and it is greater than 1, and remember the word for a number that's a number greater than 1 that's not prime, it's a composite number. So it is what does that mean? It means it can be decomposed or broken into a product of two numbers, two integers. Neither equal to that number. Why is that? Because if the only way to factor it would be to have one of the factors that same number, not another number, that same number, what does it say about that number? If the only way to factor it is to have that same number, then of course the complementary factor would have to be 1. That number would be a prime. So suppose the composite number n is greater than 0 can be written in factored form. Since it's a composite, it's not a prime, it can be factored into 2 factors, say n sub 1 and n sub 2. Okay. So at the beginning here, if n is already a prime, okay, we're done. Then it's a prime. If n is not a prime, then it's a composite. So it can be written as n sub 1 times n sub 2. Well, okay. I could work with either n sub 1 or n sub 2 or both, but it's sufficient to work with n sub 1, so I'll just work with n sub 1. So if n sub 1 is itself a prime, then n, here it is underlined, then n has a prime factor, n sub 1. And again, but we just showed this lemma. So n sub 1 divides, or is a factor of, remember we use different synonyms, n sub 1 over here divides n, see, n in the box there, n equals n sub 1 times n sub 2. So n sub 1 divides n. So n sub 1 is strictly less than, not less than or equal to. Again, it has a prime factor. Look at these parentheses, which is not n itself. So n sub 1 is strictly less than n. That's if this n sub 1 is a prime. Then n has a prime factor n sub 1. Okay, well, if n sub 1 is not already a prime, if you haven't gotten down to primes, well then it has a prime factor. And again, since it's not a prime, this prime factor will be less than n sub 1. So n sub 1 get rid of the word prime here. We don't know that it's prime yet. It may not be. But it does have a factor. If it's not a prime, then it's a composite. So it has a factor less than itself. N sub 1, we used N sub 1, N sub 2. Let's call this N sub 3 times N sub 4. Well, again, where N sub 1 was bigger than N was bigger than N sub 1, and now over here less than N sub 1. N sub 1 is greater than N sub 3. Okay, well, if N sub 3 is a prime, then N, which it equals N sub 1 times N sub 2, which now equals N sub 1 over here. N sub 1 is N sub 3 times N sub 4 times N sub 2. Showing that now N sub 3 So if N sub 3 is a prime, then N sub 1, so N sub 3 is a factor of N, then N sub 3 is a prime factor of N, then N has a prime factor. Okay, well, so now we repeat this. So we said here if N sub 3 is a prime, then N has a prime factor, namely N sub 3. But if N sub 3 is not prime, factor it into two smaller factors. What are you up to? N sub 5 and N sub 6. So we'd have N sub 3 equals N sub 5 times N plus 6 with N sub 5 less than N sub 3. So when we keep doing this, we get a succession of positive numbers N, which was greater than N sub 1, which was greater than N sub 3. Now we're up to N sub 5, greater than N sub 5, greater than, etc. And these are all positive. Last week we talked about Fermat's method of infinite descent. This can't go on forever. Eventually, try writing that a little better. Eventually, you'll get to a factor that that you can't do this to anymore, that can no longer be factored further. That is, it'll be a prime. Which is a factor of the original n. Okay, this is actually very simple. Again, it takes longer to write than to say summary.
Professor?
Yep.
On the line where you wrote n equals to n1 times n2 equals to n3 times n4, did you miss a n2?
You mean over here?
No. The line where you're writing go up to.
Oh, here?
Yes. Did you miss a n2?
Yes, I did. Yeah, the n2 carries over.
Yeah.
Thank you.
You're welcome.
But again, you don't say equals to, you just say equals. Yeah, so yeah, that n4 is there. Thank you. Okay, so look at what's happening here. It's really very simple. So if you break up n into n sub 1 times n sub 2, n sub 1 is smaller than n. If it's prime, fine, you're done. If it's not, you can break it up further into two other factors, but those factors are smaller. And if one of them, say the first one, isn't a prime, it can be broken into in 7 times n, 8 times, what are we up to, n 5, I guess we need an n5 there. But the point is, I don't sort of want to get bogged down in the notation with all the subscripts. Just look at it, visualize it, forget about the subscripts and so on. If you have let's take an example. Let's take 84. Okay, 84 either is a prime or has a prime factor. Oh, it's not a prime number. It's an even number. So we'll break it up into 2 factors, which I was calling n sub 1 and n sub 2. However you think of factoring this here, 21 times 4. Now you look at either factor. Let's look at the first one, which is what I've been doing. As I said, it suffices to just concentrate on the first one, but you can use either one. We could switch the order, but let's look at 21. So we say, is 21 a prime already? In which case, 84 has a prime factor. It's 21 times something, or not? Well, no, 21 is not a prime number, but see, it's smaller than 84 because 84 is not a prime, so you can actually break it into 2 smaller factors, 21 times 4. Okay, so the 21 is not a prime, so we factor it further. 3 times 7 times 4. And again, the fact that I can work with 4, it doesn't matter. As long as I get a prime factor here, showing that 84, while not a prime itself, has in fact a prime factor. Three. Or 7. Or if you worked with the 4 or 2. So that's all I'm doing. I'm starting with a number. If it's not a prime, it breaks down into 2 smaller factors. Look at one of them, say the first one. If that's a prime, you're done. If it's not a prime, break it down into 2 smaller factors. So now you've gotten an even smaller factor, which is still a factor of the original number. And if it's a prime, you're done. If it's not a prime, keep on factoring. And each time you factor it into smaller numbers, you get smaller numbers, but they're all positive. Because we're just working with positive numbers here. As we did in the lemma, if you have a positive number and one of the factors is positive, the other has to be positive. So you just get a succession over here of smaller and smaller positive numbers. And Fermat's method of infinite descent, so it's the impossibility of going down forever, says that your initial supposition over here, if n is not a prime, then it has a prime factor, and then that each one of those factors either is a prime or it has a prime factor, and then you get another pair of numbers, one of which either is a prime, or if not, it factors further into smaller numbers. And Fermat's method of infinite descent says this process in the box here can't go on forever. So ultimately, you have to reach a point at which you get one of these, I'll say first factors. Again, it doesn't matter which factor you use. I'll just say one of the first factors is no longer factorable, because if it were, it would factor into smaller numbers, and that cannot go on forever. So there has to be a certain point at which it comes to a stop. You can't factor it any further. At that point, you have a prime factor. Again, none of this is profoundly difficult, but it's not just a snap either, where you glance at it, of course that's it. It requires some thought. But thinking is good for you. So now And we will be seeing, including, I guess, Thursday, why we're sort of harping on prime numbers and why they're so important. I mean, they're important in many ways. There are a lot of theorems about it. There are a lot of unknown statements about them, some of which we've mentioned, and I will again. But actually, it turns out that the prime numbers are fundamental to all of mathematics in a way that we'll see on Thursday. So I may once have told you that when I was in the ninth grade and first learned about prime numbers, our homework assignment, or maybe just part of the homework, was to list all the prime numbers from 1 to 100. I don't know whether the teacher made it clear that we weren't counting 1 as a prime number, but in any case, so I don't know how much I realized of this, but so 2 is a prime number. And then after that, any multiple of 2, any even number, will not be a prime anymore. 4, 6, 8, 10, 52, 58, 60. So right there, once I've identified 2 as a prime number, I can strike out all the even numbers, and I don't have to look at 100 numbers anymore. I've halved the amount of work. I just have to look at the odd numbers. And now you look at 3. Okay, 3 you see pretty quickly is a prime number, but then you also realize that, well, by definition of prime, any multiple of 3 has a factor of 3, so it's no longer a prime. Any higher multiple of 3 itself is a multiple of 3, but any higher multiple of 3. So you get rid of 3, you leave 3, that's a prime, but all multiples of 3 will no longer be prime. So you get rid of 6, 9, 12, 15, 18, and so on. Okay, so you're rather quickly reducing the number of numbers you have to check for primeness. 4 is already out. You look at 5, now you go through the list up to 100 or whatever you're looking at, and get rid of all the multiples of 5, 10, 15, 20, 25, and so on. And then likewise, 7 you preserve, that's a prime. So far we're saving 2, 3, 5, and 7, but now you get rid of all the multiples of 7 that you've not already gotten rid of. Of course, you've already gotten rid of 14 because it was even, and we've gotten rid of 21 because it has a factor of 3. 28 is out. 35 is out, but any other multiples of 7. So the question is, how far do you have to go to not have to go any further? And the answer is given by the sieve of Eratosthenes. And I think I mentioned this earlier. So a sieve is something like a strainer with holes at the bottom so you can sort of shake out smaller particles and keep what you want. So this shakes out non-primes and leaves only primes. And Eratosthenes, these people about maybe Euclid, Eratosthenes, something like 2,500 years ago. I think I mentioned, I certainly did in geometry last term, that Eratosthenes used some actually rather elementary geometry having to do with corresponding angles of parallel lines in Euclidean geometry to measure the circumference, and hence using the formula C equals 2 pi r, the radius, right? If you know, he measured the circumference of the Earth by looking at the shadow of a vertical stick at 2 different points on a direct north-south line at noon on the first day of summer. It could actually have been any day, but when the sun is at its highest. This was in Egypt, and using a little elementary geometry from high school geometry, he was able to get a very good estimate of the circumference of the Earth. And then, as I say, once you know the circumference, you can put it into the formula C So that's known equals 2 pi. That's known r, solve r, and then you get the radius and hence the diameter of the Earth. Anyway, so this is actually a theorem. Called the sieve of Eratosthenes. Suppose we want to know whether the positive, and again, it suffices to work with positive numbers because negative numbers work the same way. You just take out a factor of -1. Given the positive number n, let I be the biggest number, the largest number whose square, you'll see why we're using this, so I is going to be the largest number whose square does not exceed n. So the square of any larger number will be more than n. So I is the biggest number whose square is not bigger than n. So if you take a bigger number, then it's not less than or equal to n, it's bigger than n. So for instance, I plus 1 squared will not be, look at this, I squared is less than or equal to n, and that's the biggest number that's less than, whose square is less than or equal to n. So if you take a larger number, I plus 1 n squared, you get more than n. Let's put that into a box. We'll come back to it. All right, so I plus 1 squared is more than n because I is the biggest number whose square is less than or equal to n, so a bigger number squared will be bigger than n. Now let's take a look at we'll prove this and then do an example. So the theorem says if no prime number, so you just have to look at the primes, that's less than or equal to I is a factor of n, then n is a prime number. So let's interpret that. So what is this really saying? To see if a number n is prime, all you have to do is check to see if the primes whose squares are less than or equal to n are factors of n, whether they divide n. If not, n is a prime. And let's give an example right now. Example. And we'll do the proof. Is say 47 a prime? All you have to do is check the primes whose squares are less than or equal to 47. See whether the primes, which are 2, 3, and 5, make that plural, the primes 2, 3, and 5, whose squares are less than or equal to 47 are factors of 47. In other words, divide 47. Let's observe that 7 is too big. We're not going to check that. 7 squared is not less than or equal to 47. So we're not going that far. Well, okay, so let's see. No, well, 2 does not divide or is not a factor of. Semicolon. And you can quickly see that neither is 3. 3 times 16 is 48, so 48 is divisible by 3, 47 isn't. And five isn't a factor of it. It doesn't divide 47. It's not a factor of 47.
Professor?
Yep.
We should check 6 too. Oh, never mind.
No. You only have to check. No, if 6 were, that's good point. I'm glad you mentioned that. You only have to check the prime numbers. And the reason, let's take 6, good point. The reason you don't have to check 6 is that if 6 were a factor of 47, then 2, which is a factor of 6, it would be, instead of 6, 2 times 3, then 2 would be a factor of 47. And we've already ascertained that it isn't. So, good point. I like you thinking about, what else? So look how simple this becomes. For 47, all you have to do is check 3 numbers. You know what? Before we do the proof, let's do another example. Let's take 83. Okay, 84, 82, those are even numbers. They're divisible by 2, so they're not prime. So what about 83? So we have to see whether the primes, the positive primes, that are, well, whose squares are less than or equal to 83 are factors of, in other words, divide, if you want to look at it that way. And the sieve of Eratosthenes says the only numbers we have to check are the primes 2, 3, 5, 7, so we just have to see whether the prime numbers whose squares do not exceed 83 are factors of 83. 11 is too big. 11 is a number whose square does exceed 83, so we don't have to go that far. Okay, so we can quickly see that no, 2 doesn't divide it 3 into 83. No, 3 goes into 81. 81 is 3 to the 4th power. Or just try dividing 83 by 3. So you get 2 with 2 left over, then 23. No, it's obviously not a multiple of 5. Does 7 go into 83? Well, 7 goes into 8, 1. So you have a 1 there with 1 left over, which makes that a 13. No, 7 doesn't go into 13 since none of 2, 3, 5, 7 are factors of or divide. $83. You don't have to check any other numbers. 83 is a prime number. So again, that certainly makes things much easier. So close those parentheses. All right, so now let's go back to the proof. Okay, so put it into a box again. Okay, so let's repeat this. We are supposing that this is true, and then we're contending that n is a prime number. Okay, so the claim is that n is a prime, like 83 was a prime, if no prime number whose square is less than or equal to 83 is a factor of 83. So n is a prime if no prime less than or equal to I squared is a factor of n. Okay, so suppose that's the case. Suppose sorry, it's just, let's see, claim if no prime less than or equal to I where I squared. So get rid of the, yeah, it's less than or equal to I where I squared is less than or equal to, maybe I should have rewritten that. If no prime less than or equal to I is a factor of n, I'll put it in here. So suppose no prime whose square is less than or equal to n, where less than or equal to I, where I is the largest number such that so again, looking at this box, so I is the largest number whose square is less than or equal to n. So any larger number than I, like, look in the box here, like I plus 1 squared is going to be bigger than, not 0, than n. Okay, that's what we had up here. I plus 1 squared is bigger than n because I is the biggest number whose square is less than or equal to n. So a bigger number, I plus 1 in the box, squared is more than 1. And I claim that n is prime if no prime number less than or equal to I, where I is the biggest number whose square doesn't exceed n, is a factor of n. That's the claim. So suppose not means we're going to do it by contradiction. Suppose contrary to the claim here with the arrow, the claim is that n is prime. Suppose not. Suppose contrary to that, n is not a prime. In other words, it is a composite number. And what do we try to do? We try to get a contradiction. Okay, from the lemma, since we are supposing, as a supposition,
Professor.
Yeah.
Nobody knows what's a lemma.
What? Okay, what were you saying?
It was answered in the chat. Thank you.
What? You have it? It's okay?
We're asking for the definition of lemma, but which is a proof done from before, correct?
Yeah, the lemma at the top here, which I'm going to repeat. So the I called it a theorem. Okay, from the theorem. I mean, a lemma is a theorem. From the theorem of the top, since we're assuming n is not a prime, what the theorem says is, well, then it has a prime factor. Here, let f be the complementary factor. Okay, so then the hypothesis is that P so we're assuming that P is not a prime, so it has a prime factor, but P has to be greater than or equal to I. So we're assuming that no prime that's less than, make that clearer. Okay, we're assuming that we're saying there's no prime who's over here, the claim that claim that n is a prime if no prime less than or equal to I is a factor of n. So suppose no prime whose square is less than or equal to I. Is that sentence complete? Where no factor whose square is less than or equal to I, where I is the biggest factor such as I equals n, is a factor of n. So P must be greater than I, because no prime whose square is less than I is a factor of n. So P has to be greater than I, and so P has to be greater than or equal to I plus 1. Now let's look at F. F also has to be greater than or equal to I, because according to the theorem, it either is a prime or has a prime factor. And again, since, like in the previous parentheses, since we're assuming that no prime less than or equal to I is a factor of n, F has to be greater than or equal to I, because F either is a prime or has a prime factor, which by hypothesis is not less than or equal to I. So F is greater than I. F has to be at least I plus 1. I'm using that to mean inequalities. Namely, P is greater than or equal to I plus 1. That's this one. And then F is greater than or equal to I plus 1. But we are assuming that n is not a prime, so n can be written as p times f. But p is greater than or equal to I plus 1 times f is greater than or equal to I plus 1, which equals I plus 1, the whole thing squared. So what we have here is n is greater than or equal to I plus 1 squared. So up here in the first box, we have that n is less than I plus 1 squared. Let's keep it the same order. So in this first box over here, n is less than I plus 1 squared, but over here, n is greater than or equal to I plus 1 squared. Contradiction of the trichotomy law that says a number is either less than another number or greater than or equal to it. It can't be both. So the assumption or supposition that n was the composite p times f was wrong. N is not a composite because the assumption that it was led to a contradiction. Notice how lead is spelled the past tense of lead. The past tense of read is read. and spelled the same way, but the past tense of lead is pronounced the same way, well, as read, but it's doesn't have the A. Anyway, and so we conclude after our spelling lesson, the theorem is established. If n is not divisible by, doesn't have a factor of, by any prime whose square is less than or equal to n, then n is a prime number. Okay, I wanted to also establish today that there's an infinite number of primes. That proof is not too lengthy, but it's important to look at. And so maybe for a change, we'll end more or less on time and not pursue that further now, but defer that until Thursday. And also hope to pursue that to the fundamental theorem of arithmetic, where arithmetic is means theory of numbers. So I'm going to get out of this, come back to you, see if there's anything you want to discuss, and if not, we will adjourn and reconvene on Thursday. So let's get out of this. And